Now I would like to discuss the regions of the periodic table. The periodic table is so useful. I cannot overemphasize how useful it's going to be to you guys throughout your experience in general chemistry. And it provides a wealth of information on all the different elements, and there's a lot that you can figure out from it about their fundamental properties. So I want to introduce you to it step by step. This is the periodic table of the elements, and you'll notice here that there's a thick line between boron and aluminum, and between silicon and aluminum, and silicon and germanium, and arsenic and antimony, and tellurium and polonium and astatine. That thick diagonal staircase separates the two major categories on the periodic table, which are on the left side, the metals. So everything to the left of that diagonal staircase is a metal. And on the right side of that diagonal staircase, we have the nonmetals. So those two categories are extremely important in just separating the elements. Now, what we'll find out in subsequent chapters is that metals tend to form cations, and nonmetals tend to, but not always, form anions. The other thing you should know is that elements that touch the diagonal staircase directly, okay, so the ones that are right on the diagonal staircase, boron, aluminum, silicon, germanium, arsenic, antimony, tellurium, and polonium, these are called metalloids or semimetals. So the way that you spell that is M-A-L-L, metalloids like that, or semimetals. Those are elements that touch the diagonal staircase, and they kind of have in-between properties in between metals and nonmetals. For example, you can see germanium can form cations as well as anions. So I want to break down the periodic table just a little bit further so that we can start making some definitions. As we've said before, just to review, the periods in the periodic table are the horizontal rows, and the groups are the vertical columns in the periodic table. And we talked about how elements in the same group share similar chemical properties. Now, when you look at this periodic table, it has the group numbers here, 1, 2, 3, 4, 5, 6, 7, 8, etc., all the way across the periodic table. In some older periodic tables, you will find these as Roman numerals. So you'll sometimes see this as group 1A with a Roman numeral, this as group 2A. And then over here, 13 is 3A. And then you would have 4A, how's 4? IVA, and then 5A, etc. 6A, 7A, and 8A. You'll see that in some older periodic tables. That's because these groups here, now I'm going to really start messing with my periodic table, 2A, 3A, and then all of these groups here, the 3A through 8A, those are called the main group elements. So I want to talk about, and then that's to distinguish them from these transition metals in the D block and the lanthanides and actinides in the F block. I want to talk about the main group elements in a little bit more detail for just a second, because it's good to kind of know about their particular characteristics. So the main group elements are groups 1A in the Roman numeral nomenclature to 8A, or 1 to 2, and 13 to 18 in the newer nomenclature. So group 1/1A. These are known as the alkali metals. And if you look at them, strictly speaking, hydrogen actually doesn't really belong to the alkali metals. Hydrogen is actually a non-metal, and oftentimes, sometimes you'll see it in the periodic table over here to emphasize the fact that it's a non-metal. But strictly speaking, the alkali metals encompass lithium to francium. And you'll notice if you zoom in that they always form +1 cations when they are in compounds. You see that? So remember how we said that atoms or elements that share groups on the periodic table have the same or similar chemical behavior? This is an example. They're always forming +1 cations. So in compounds, you're going to see sodium, potassium, lithium, etc., forming +1 cations. As we go across the periodic table, we have group 2 or 2A. These elements are known as the alkaline earth metals. And those metals always form, you can see this from the periodic table, +2 cations. They want to lose their 2 valence electrons to be more like the noble gas nearest to them. So, for example, there you would have calcium 2+, magnesium 2+, etc. These alkaline earth metals always are forming 2+ cations. Going all the way over to group 13, so this is now in the metalloid / non-metal metal border of the periodic table. It's also known as group 3A. Those elements form +3 cations. One of the most typical ones is aluminum, which you're always going to see in the 3+, with a 3+ charge when it forms chemical compounds. So you can kind of predict what the behavior is going to be. For group 14, also known as 4A, those elements are usually, but not always, +2 or +4. It really depends on the element. And some of them can also be anions. Group 15, also known as 5A, now you start getting anions. So 5A would be looking at nitrogen, phosphorus, arsenic, antimony. Usually when these are in compounds, they'll gain 3 electrons to be more like the nearest noble gas, but they can kind of also form cations. It depends on what compound they're in. They have very interesting chemical behavior. So they're usually -3, but not always. Group 16 are a special group called the halcogens. And this group is usually -2 because they want to gain 2 electrons to be like the closest noble gas. However, they can also form cations even as you get further down the periodic table. So it just kind of depends on what compound you're talking about. With a lot of the nonmetals, their behavior changes a lot. They can form anions or cations and often go in both directions. Group 17 are the halogens. Halogens literally means salt formers in Greek. And those are usually, but not always, in the -1 state because they gain an extra electron to become like the nearest noble gas. So I didn't provide examples here, but here nitrogen 3-, phosphorus 3- would be good examples of group 15. Sulfur 2-, oxygen 2- are great examples of group 16. And for the halogens, we have fluoride, chloride, bromide, iodide. typically we have them forming -1 anions. And the reason why they're called salt formers is because they often are the anionic components in salts. For example, sodium chloride. Finally, the last group in the main group is group 18, also known as 8A. And that group are the noble gases. Sometimes you'll hear the noble gases referred to as the inert gases because they do not tend to form ions. They tend to be unreactive. They tend not to form ions. They don't want to ionize because they already have a very stable electron configuration. All right, so just going back for a moment to the periodic table to finish up our discussion. In fact, let me get a nice clean periodic table so that we can start over with a nice clean slate. So going back to the periodic table for a moment, I want to draw your attention to a few other vocabulary words. All right, so we have the nonmetals on the right and the metals on the left. Oh, one thing I should mention is that what's the definition of a metal? Metals are elements that conduct electricity, and nonmetals do not. That's the definition. That's what separates nonmetals from metals, is their conductivity. So that's where that definition kind of comes in. And conducting electricity involves having electrons move through the material. So a few other things. We define the main group elements, but I know we've talked about this before, but I just want to highlight groups 3 through 12. These are known as the transition metals. They are always cations, but they tend to take variable charges. And we also call them the D block because they correspond to filling up the D orbitals in atoms. Then the other important elements are the F block. So the transition metals are the D block elements. Down here, we kind of have lanthanum. Going down here, we have the lanthanides and the actinides. And these correspond to the filling of the F orbital. So we call this the F block. So that first row here, these are the lanthanides, just because that series starts with lanthanum. And this is the actinides. Okay, so that's pretty deep in the periodic table. So the transition metals, the lanthanides, and the actinides are not part of the main group. They're part of the D block and the F block, and they correspond to the filling of those orbitals. We will put this into practice a lot in chapter 3 when we start talking about different kinds of compounds that form, ionic compounds in particular. All right, that's it.